Hello friends, in today's lecture we shall be talking about the memory devices. In computer terminology, memory usually refers to RAM and ROM, and storage refers to hard disk, floppy disk and CD-ROM. Computers and other types of systems require the permanent or semi-permanent storage of large amounts of binary data. Microprocessor based systems rely on storage devices and memories for their operation because of the necessity for storing programs and for retaining data during processing. The memory devices covered in this lecture are generally used for longer term storage of larger amounts of data than registers can provide. The focus in this discussion is the memory logic portion of the system, which stores the entry code. Once the memory logic is developed, it is interfaced with the security code logic to form the complete system. After completing this and the next lecture, you should be able to define the basic memory characteristics, explain what a RAM is and how it works, explain the difference between static RAMs and dynamic RAMs, explain what a ROM is and how it works, describe the various types of PROMs, and finally discuss the characteristics of a flash memory. Basics of semiconductor memory. Memory is the portion of a system for storing binary data in large quantities. Semiconductor memories consist of arrays of elements that are generally either latches or capacitors. As a rule, memories store data in units which have from 1 to 8 bits. The smallest unit of binary data, as you know, is the bit. In many applications, data are handled in 8-bit unit called a byte or in multiples of 8-bit units. The byte can be split into two 4-bit units that are called nibbles. A complete unit of information is called word and generally consists of one or more bytes. Each storage element in a memory can retain either a 1 or a 0 and is called a cell. Memories are made up of arrays of cells as illustrated in this figure using 64 cells as an example. Each block in a memory array represents one storage cell, and specifying a row and a column can identify its location. The 64 cell array can be organized in several ways based on units of data. Figure shows an 8 into 8 array which can be viewed as either a 64-bit memory or an 8-byte memory. Part B shows a 16 into 4 array which is a 16 nibble memory, and part C shows a 64 into 1 array which is a 64-bit memory. Memory addresses and capacity. The location of a unit of data in a memory array is called its address. For example, in figure A, the address of a bit in the two-dimensional array is specified by the row and columns as shown. In figure B, the address of a byte is specified only by the row. So, as you can see, the address depends on how the memory is organized into units of data. Personal computers have random access memories organized in bytes. This means that the smallest group of bits that can be addressed is 8. The figure here shows that the address of a byte in a three-dimensional array is specified by the row and column. In this case, the smallest group of bits that can be accessed is 8. The capacity of a memory is the total number of data units that can be stored. For example, in the bit organized memory array in figure A, the capacity is 64 bits. In the byte organized memory array in figure B, the capacity is 8 bytes, which is also 64 bits. Basic memory operations. As indicated in figure, the data bus is bidirectional, which means that the data can go in either direction, that is, into the memory or out of the memory. In this case of byte organized memories, the data bus has at least 8 lines, so that all 8 bits in a selected address are transferred in parallel. For a write or read operation, an address is selected by placing a binary code representing the desired address on a set of lines called the address bus. The address code is decoded internally and the appropriate address is selected. In the case of a 3-dimensional memory array as shown in figure, there are 2 decoders, one for the rows and one for the columns. The number of lines in the address bus depends on the capacity of the memory. For example, a 15-bit address code can select 2 to the power 15 locations in the memory. A 16-bit address code can select 2 to the power 16 locations in the memory, and so on. In personal computers, a 32-bit address bus can select 2 to the power 32 locations expressed as 4G. The write operation. A simplified write operation is illustrated in figure. To store a byte of data in the memory, a code held in the address register is placed on the address bus. Once the address code is on the bus, the address decoder decodes the address and selects the specified location in the memory. The memory then gets a write command and the data byte held in the data register is placed on the data bus and stored in the selected memory address, thus completing the write operation. When a new data byte is written into a memory address, the current data byte stored at that address is overwritten, that is, replaced with a new data byte. The read operation. A simplified read operation is illustrated in figure. Again, a code held in the address register is placed on the address bus. Once the address code is on the bus, the address decoder decodes the address and selects the specified location in the memory. The memory then gets a read command and a copy of the data byte that is stored in the selected memory address is placed on the data bus and loaded into the data register, thus completing the read operation. When a data byte is read from a memory address, it also remains stored at that address. This is called non-destructive read. RAMs and ROMs. The two major categories of semiconductor memories are the RAM and the ROM. RAM, known as random access memory, is a type of memory in which all addresses are accessible in an equal amount of time and can be selected in any order from a read or write operation. All RAMs have both read and write capability. Because RAMs lose stored data when the power is turned off, they are volatile memories. ROM, known as read-only memory, is a type of memory in which data are stored permanently or semi-permanently. Data can be read from a ROM, but there is no write operation as in RAM. The ROM, like the RAM, is a random access memory but the term RAM traditionally means a random access read-write memory because ROMs retain stored data even if power is turned off. They are non-volatile memories. Random access memories. RAMs are read-write memories in which data can be written into or read from any selected address in any sequence. When a data unit is written into a given address in the RAM, the data unit previously stored at that address is replaced by the new data unit. When a data unit is read from a given address in the RAM, the data unit remains stored and is not erased by the read operation. This non-destructive read operation can be viewed as copying the content of an address while leaving the content intact. A RAM is typically used for short-term data storage because it cannot retain stored data when power is turned off. The RAM family. The two categories of RAM are the static RAM and the dynamic RAM. Static RAMs generally use latches as storage elements and can therefore store data indefinitely as long as DC power is applied. Dynamic RAMs use capacitors as storage elements and cannot retain data very long without the capacitors being recharged by a process called refreshing. Both static RAMs and dynamic RAMs will lose stored data when DC power is removed and therefore are classified as volatile memories. Data can be read much faster from static RAMs than from dynamic RAMs. However, dynamic RAMs can store much more data than static RAMs for a given physical size and cost because the dynamic RAM cell is much simpler and more cells can be crammed into a given chip area than in the SRAM. The basic types of SRAM are the asynchronous SRAM and the synchronous SRAM with a burst feature. The basic types of DRAM are the fast page mode DRAM, the extended data out DRAM, the burst EDO DRAM and the synchronous DRAM. Static RAMs. All static RAMs are characterized by latch memory cells. As long as DC power is applied to a static memory cell, it can retain a 1 or 0 state indefinitely. If power is removed, the stored data bit is lost. Figure shows a basic SRAM latch memory cell. The cell is selected by an active level on the select line and a data bit 1 or 0 is written into the cell by placing it on the data in line. A data bit is read by taking it off the data outline. The memory cells in a SRAM are organized in rows and columns as illustrated in this figure for the case of an n into 4 array. All the cells in a row share the same row select line. Each set of data in and data out lines go to each cell in a given column and are connected to a single data line that serves as both an input and output through the data input and data output buffers. To write a data unit, in this case a nibble, into a given row of cells in the memory array, the row select line is taken to its active state and 4 data bits are placed on the data input output lines. The write line is then taken to its active state, which causes each data bit to be stored in a selected cell in the associated column. To read a data unit, the read line is taken to its active state, which causes the 4 data bits stored in the selected row to appear on the data output lines. Dynamic RAM memory cells. Dynamic memory cells store a data bit in a small capacitor rather than in a latch. The advantage of this type of cell is that it is very simple, thus allowing very large memory arrays to be constructed on a chip at a lower cost per bit. The disadvantage is that the storage capacitor cannot hold its charge over an extended period of time and will lose the stored data bit unless its charge is refreshed periodically. To refresh, it requires additional memory circuit, which complicates the operation of the DRAM. Figure shows a typical DRAM cell consisting of a single MOS transistor and a capacitor. In this type of cell, the transistor acts as a switch. The basic simplified operation is explained through these figures. A low on the read-write bar line enables the tri-state input buffer and disables the output buffer. For a 1 to be written into the cell, the D in line must be high and the transistor must be turned on by a high on the row line. The transistor acts as a closed switch connecting the capacitor to the bit line. This connection allows the capacitor to charge to a positive voltage. When a 0 is to be stored, a low is applied to the D in line. If the capacitor is storing a 0, it remains uncharged, or if it is storing a 1, it discharges as indicated in the figure. When the row line is taken back low, the transistor turns off and disconnects the capacitor from the bit line, thus trapping the charge 1 or 0 on the capacitor. To read from the cell, the read-write bar line is high, enabling the output buffer and disabling the input buffer. When the row line is taken high, the transistor turns on and connects the capacitor to the bit line and thus to the output buffer, so the data bit appears on the data output line. For refreshing the memory cell, the read-write bar line is high, the row line is high and the refresh line is high. The transistor turns on, connecting the capacitor to the bit line. The output buffer is enabled and the stored data bit is applied to the input of the refresher buffer, which is enabled by the high on the refresher input. This produces a voltage on the bit line corresponding to the stored bit, thus replenishing the capacitor. So friends, that brings us to the end of our discussion in this lecture, and therefore we sum up. In this lecture, we learned that bit is the smallest unit of data. A write operation stores data in memory. A read operation takes a copy of data from memory. A unit of data is located by its address. A RAM is a volatile and has a read-write capability. A ROM is non-volatile and has only read capability. A RAM is a small fast memory between the CPU and main memory. SRAMs have a latch storage cells that can retain data indefinitely while power is applied. DRAMs have capacitive storage cells that must be periodically refreshed. The refresh operation prevents data from being lost because of capacitive discharge. So that is it for today. See you in the next lecture with more on digital circuits. Thank you very much.